Hello everyone, my name is Mihaela Ștefan. I am a professional services engineer at Infinet Wireless. Thank you very much for taking the time to join our webinar. Today we are going to discuss in detail about interference, and I will also point out how interference can be useful in case of NLOS deployments. The agenda for today includes two main topics. First, I will define interference and will review what are the factors causing it. Then we will introduce step by step the available interference mitigation techniques implemented by our Infinet Wireless devices. Let's see to what are we referring when we talk about interference. As you know, the wireless signal is an electromagnetic wave that propagates through the air. On its way, the signal will reflect and diffract on different objects, generating replicas that are most likely out of phase. For example, it will face meteorological phenomena, and as the air is a shared medium, it will also encounter other radio signals that are correlated with its characteristics. The radio signals that are not correlated with the characteristics of the signal will be simply viewed as background noise that also affects the quality of your transmission. Interference is a phenomenon specific to waves, and the basic concept is that if multiple waves are present in a location, they will sum up together constructively or destructively, creating a new distorted resultant signal. Therefore, if we generate a good-looking signal, like we see on the transmitter side in our picture, after being exposed to the propagation channel, it will reach the receiver in a distorted version. The scope of the interference mitigation techniques is to take measures against the factors causing interference and to help the receiver recover the useful data from the distorted received signal. Usually, the methods that are implemented at transmission are preventive, and the ones implemented at the reception are corrective. Let's briefly review the factors that cause interference and signal distortion. The first one is the natural interference that includes the atmospheric phenomena and the weather conditions in general. The atmospheric phenomena can lead to a change in the path of propagation. For example, the higher we go into the atmosphere, the colder it should be. However, if the pressure is very high in a certain layer, an increase in temperature will occur, and we will have a warm, dry air over a cold surface. This warm surface will act like a duct and reflect the signal in different directions. In general, the changes in the atmospheric pressure will directly influence the propagation of the electromagnetic waves. And another factor to be taken into account is the sea breeze that also modifies the properties of the transmission medium. Next, the weather conditions are also of great importance. Interference can be caused by electrical processes taking place in the atmosphere, mainly during lightning discharges, or it can be caused by precipitation in the form of rain, snow, and others. Rain, fog, and lightning will cause absorption and interference, and the higher the frequency, the more significant the impact of the rain on the communication channel will be. So bear in mind that high frequencies are very sensitive to absorption, and the communication strongly depends on the weather conditions. You can see in the picture the results obtained during the outdoor tests performed for Quanta 70. When the weather is sunny and stable, high throughputs are obtained over distances of up to 11 kilometers. But as the rain becomes more heavy, the signal is absorbed and lower modulation encoding schemes are available, leading to much lower throughputs as the distance increases. Let's now discuss about the artificial interference factors, which can be artificial obstacles or industrial interference. I will show you their influence onto our communication signal. The communication between two devices can be established in non-line of sight conditions because of the diffraction effect. In other words, because the signal is bending around an obstacle. The diffraction effect is illustrated in the picture. The Fresnel zone between the receiver and the transmitter is blocked by the building. However, the radio signal from the transmitter goes around the corner of the building, changes direction, and reaches the receiver. Please note that the signal's energy will be scattered into the medium because of diffraction, leading to a decrease of the maximum distance compared to the line of sight conditions. For example, if the signal does not reflect when meeting an obstacle or does not go around the corners or doesn't penetrate the object, then the signal is considered to be absorbed. Different materials absorb the radio signal differently. For example, bricks and concrete walls will absorb the signal well enough, while a dry wall will not absorb it very good. Absorption results in a significant attenuation of the signal. So the amplitude of the current at the receiving antenna depends on what part of the transmitted power was absorbed. Another factor is the reflection of the signal in the presence of water surfaces, buildings, or planes. If the radio signal meets an obstacle which in size exceeds the wavelength, the wave reflection effect will appear. This effect can also be used in order to establish the communication in non-line of sight conditions, as it can be seen in our picture. You can take advantage of the signal reflected by the neighboring building, but please remember that interference can also be destructive. So in a place where multiple reflections occur, like business centers or near the surface of the water, a careful analysis of the signal at the reception must be performed in order to evaluate the possibility of establishing an efficient radio communication system. In the picture, you can see an example of an NLOS deployment using the Quanta 5 model. Multiple obstacles are present in the Fresnel zone, some along the path and others right in front of the radio units. As you can see in front of location A, there are trees that absorb the signal, and in front of location B, there is a building obstructing the path. Even if there is no direct visibility, the link was established over a distance of 700 meters in good conditions, thanks to the reflection and diffraction effects. So NLOS deployments are proven to work fine in the field if the necessary conditions are met. Moving forward, scattering is another effect that works in the opposite way to absorption. If the obstacle on the propagation path is smaller than the wavelength, then the electromagnetic wave is reflected from this object in all directions. Such an effect can be encountered during the propagation of a signal in rainy weather or through a coniferous forest. The disadvantage in case of scattering is that there is no specific preferred direction in which the energy is redirected, as the energy is dissipated equally in all directions. In a multipath scenario, the reflection effect appears many times. So at the receiver side, many copies of the signal will arrive at the same time, but coming from different paths, as it is shown in the figure. This is the multipath effect represented in the picture. The reflected signal can differ from the original one by its parameters: amplitude, frequency, phase, and polarization. In the figure, the red and green lines show the copies of the signal on the receiving side, phase shifted due to having different propagation times, and the blue line shows the resulting signal. In the first case, the phase shift of the signal is between 0 and 120 degrees, so the resulting amplitude exceeds each of the received copies. And in the second case, the shift is between 121 and 179 degrees, so the amplitude of the resulting signal is below the received copies. While in the third case, the received copies are in antiphase, so the resulting signal is 0. This is the most unuseful situation. More often, in dense developments, a great amount of signal copies reach the receiver, and the resulting signal is distorted as illustrated in the picture. So this is how it actually looks, a real signal received in dense multipath mediums. Let's now move forward and discuss about the electromagnetic emission sources. As you know, the interference caused by the simultaneous operation of several radio equipment in a common frequency range is called mutual interference. This arises when the frequency spectrum of some devices lays within the reception bandwidth of other devices. This leads to electromagnetic compatibility problems. Different radio equipment operating in the same frequency range and having similar signal characteristics is represented, for example, by the Wi-Fi, LTE, and WiMAX systems operating in the same location. It is necessary in such cases to install the antennas as far as possible from one another, the recommended distance being at least 2 meters between the edges of the antennas. In the picture, you can see the frequency spectrum of 3 communication channels. Since channels 1 and 2 overlap, this will lead to negative consequences in the form of what we call mutual influence. Channel 3 doesn't overlap with any of the communication systems, and there is also a guard interval between channels 2 and 3, and this is the best scenario. The usage of the frequency resources is governed by the state policy, so an important aspect in the operation of the wireless communication systems is the authorization from the state authorities and the usage of certified equipment. Since the devices operating on adjacent frequencies can have influence on each other, an important indicator is the frequency mask that determines the allowed level of out-of-band radiation. You can see in the picture the frequency masks for different channel bandwidth. It is important to notice that you can use an equipment with a radiation that is 20 dB lower than the in-band signal's power. And it should also be noted that the radiation requirements become stricter when increasing the distance from the center frequency of the channel. The out-of-band radiation must be very low when we go far from the center of the channel. An important link quality indicator is the received SNR. If the transmitter's power increases, the SNR on the receiving side increases also. However, this solution has several disadvantages. The transmitter power is regulated by the state. The operation at increased powers reduces the service life of the equipment, and the out-of-band radiation level increases with the transmitted power. The out-of-band radiation level is determined by the transmitting device spectral mask, as we discussed in the previous slide, and the radiation power increase will affect the operation of the system using adjacent channels. In the picture, the orange color indicates the adjacent channel out-of-band emission. When increasing the transmission power in the adjacent channel, the interference level will also increase, as you can see in the picture below. Another type of electromagnetic radiation sources are the pulses coming from unknown sources, for example, from radars and other radio equipment operating in a different spectrum that will be seen as noise. What I want to mention is that the wireless devices should not be placed near the power lines. It is necessary to install the devices at a distance of at least 100 to 150 meters relative to the power transmission lines, having a voltage higher than 35 kilovolts. Moving forward, there are 2 main evaluation criteria for the level of interference. The first one is the signal-to-noise plus interference ratio, which you might also know as channel-to-noise plus interference ratio. As we can see in the picture, the lowest level is the noise floor, representing the background radiation, uncorrelated with the useful signal. Besides this, an in-band interference is present, and in order to correctly evaluate the quality of the channel, the signal to interference plus noise ratio should be taken into account, not just the SNR. The second criteria for determining the quality of the channel is to evaluate the bit error rate. This tells us the percentage of bits that are altered or erroneously received, and it is often defined as the ratio between the number of errors bits and the total number of bits that were sent over a specific measurement period. The interference mitigation techniques will usually measure either the SINR or the bit error rate and will try to optimize them in order to ensure a high SINR value and a low bit error rate level. This corresponds to a good transmission channel quality. So the SINR and the bit error rate are correlated and express the quality of the transmission. Let's now move forward and review the interference mitigation techniques available for the Infinet Wireless units. Let's begin with ARQ, a technology which enables the packet retransmission in case of previous unsuccessful delivery. ARQ allows to achieve a reliable connectivity even in a highly congested spectrum. Next, the devices of the Infilink 2x2 and of the Infiman 2x2 families allow you to obtain the MAC addresses of the devices operating in the selected frequency channel using the radio scanner tool. It is possible to identify the source of interference and to decide the measures in order to eliminate its effects on the link. A manual preliminary radio survey of the territory in which the communication systems will be deployed should also be performed. The frequency is selected, taking into account the results of the scanned spectrum. The Infinet devices allow you to efficiently evaluate the state of the spectrum using the built-in spectrum analyzer tool. A radio survey of the environment is also performed periodically using the automatic mode. The frequency channel can be automatically changed based on the scanned data. The Infinet devices support the DFS and instant DFS technologies, which are designed to automatically scan the spectrum, identify the interference levels, and take the necessary measures to eliminate the effects. Next, even if the distribution of the frequency channels is coordinated, the mutual interference may still persist. That happens due to the presence of an out-of-band radiation, and the automatic transmit power control function can help to reduce the influence of a third-party communication system operating in the same frequency channel. In case of interference, the devices having ATPC activated will increase the radiation power and maintain the link performance. Forward error correction is a method for preventing errors or data loss in noisy environments. It is also called channel coding, and it is based on adding redundancy bits to the data stream by using a coding scheme. This will help the receiver to better estimate the value of the received bits. Next, the link budget depends also on the used modulation and coding scheme. Higher modulation and coding schemes require higher link parameters, therefore they are impossible to use with a low signal level and a high level of interference. The modulation and coding scheme selection is practically a compromise between the link's performance and its reliability. The automatic modulation control function allows the selection of the modulation and coding scheme according to the current parameters of the radio link. This increases the reliability and the availability of the information by keeping the link operational even in strong interference conditions. We will now move forward and discuss about the MIMO and MISO modes. The Infinet Wireless units transmit and receive using the MIMO 2x2 mode. We can state the following advantages. It improves the link reliability with an increased ability to cancel the signals present in the same band, and it increases the capacity by sending parallel data streams. Near and non-line of sight performance is also enhanced. The MISO mode is also available for the Infinet Wireless units, and the significance of MISO in this case is that both antennas, vertical and horizontal, are used to send the same data stream. This will reduce the capacity to have, but if you don't have high capacity requirements, this is a very efficient way to counteract propagation phenomena like multipath fading. Since the same data is received by two antennas, it is less probable that both polarization will be subject to the same type of interference, so the original data can be easily recovered from one of the paths. Next, we'll discuss about antennas and how big is their importance in ensuring a good transmission quality. We'll review the most important aspects related to antennas that should be always considered when evaluating its performance. The front to back ratio indicates the ratio between the power gain of the front and of the rear end of the antenna. Infinet Wireless integrated antennas feature a high front to back ratio of minimum 20 dBs and reduce the interference in case of collocated devices. Another important characteristic is the VSVR, which expresses the amount of power that is reflected back to the RF chain instead of being radiated. The minimum VSVR value is 1, which represents the ideal case when no power is reflected back. A high VSVR value greater than 2, for example, will cause a significant power loss on certain frequencies and also the signal distortion that leads to retransmission and data transfer errors. The VSVR value for the Infinet units does not exceed 1.7, and it is evenly distributed over the frequency range, ensuring a proper signal quality. Moving forward, we know that a real antenna will never radiate in a pure polarization mode. The cross-polarization isolation indicates how much lower is the power level of the cross-polarized component compared to the desired polarization component. A bad antenna isolation determines unstable MIMO transmission in medium range, leading to a significant performance degradation. The Infinet Wireless integrated antennas feature minimum 30 dB cross-polarization isolation, which is very good. The polarization of the transmitted radio signal will also be influenced by the transmission medium. In its way, the signal will suffer from additional polarization shifts, and it will arrive at the receiver with a different orientation. High-performant antennas have the capability to convert the useful signal at the reception, even if the polarization was highly affected by the transmission medium. This brings us to the end of today's presentation. If you have any questions, please write them in the chat section, and I will answer them one by one. I will just have a short break of about 5 minutes, and then we will come back for the Q&A session. Thank you very much. Hello, I'm back for the questions. I see our first question is that someone tested Quanta 5 in clear line of sight, but it couldn't get a full bar signal. You must understand that clear line of sight is not the only condition to obtain a full signal. You must take into account if you have interferences, for example, because you can have a short distance link with the line of sight, but interferences can damage the link. Also, if you have a long distance link, even if you have clear line of sight, you will not have a full signal, for example, because the distance is too long. What I want to recommend is that you first try to plan the link in InfiPlanner and see if at the distance that you are having and in the terrain conditions that you have, the expected signal in InfiPlanner is met. Because if your actual signal in the field is much lower than the expected signal value reported in InfiPlanner, then you have a problem. And in this case, you should raise a case to our support team. But if the value is close to what InfiPlanner predicts, then the link is fine, even if it's not full signal, okay? So you should try to plan in InfiPlanner, see the actual expected signal value, see if you are close to it. And if you consider you have a problem, you should create a ticket to our support team. Next, we are told that there is a link over the sea and it is not stable. Yes, the problem in this case is the water reflection. You should expect this behavior near the surface of the water. It is creating many problems and it should in general not be very stable. Next, we are asked if there is a way for the device to actively scan the band and to know the frequency that is least interfered and automatically switch to it. Yes, our devices have the instant DFS feature, which is present in all our devices, but just take into account that for the R5000 devices, you should have a specific hardware revision. It's hardware dependent for the R5000, but for Quanta and XG, it is available for all the units. And it will scan the spectrum automatically and switch to the least interfered frequency. Okay, so remember instant DFS. What is the minimum separation distance required between collocated devices to avoid performance degradation? As I said during our webinar, it is 2 meters between the edges of the antenna. This is the recommended situation. You can try lower values, but if you do the tests for interference and decide that it is fine, but the recommendation is 2 meters between antennas. What causes VSVR and how can someone avoid that effect? Okay, VSVR is obtained when the device's impedances do not meet very well, when there is a mismatch between the impedance of the charge of the antenna and of the circuit. So what is recommended is to properly install the antenna and the components and make sure that the VSVR is fine. So you should have a match between the impedance of the antenna and the impedance on the circuit. Is there a problem if we put maximum power on short distance? First of all, you should check if you are allowed to use that maximum power in your country. And then you should see if there are other equipment of radio systems, for example, working in the area, because you might interfere them. If your country regulation allows the maximum power that you want, you can use it, but you must take into account that you will increase interference in the area. So you might have complaints from other systems. Other systems may have automatic transmit power control, and if they detect that your power is increased, they will automatically increase their power also and will interfere with your system as well. So you can try to put the maximum allowed power, but you should see if you have consequences or not, because other systems operating in the area might increase their power as well automatically if they detect your signal. We are asked if external antennas are available. Yes, our units come in 2 models, with integrated antennas and with connectors for attaching an external antenna to achieve longer distances. And then we are asked what is the maximum distance for a point to multi-point base station. It is 36 kilometers, the maximum distance achieved in point to multi-point. Okay, I will switch to the chat section. For a 200 kilometers link, if we recommend Quanta 5 with external antenna or XJ1000, we recommend Quanta 5 for such distances. You cannot use XG1000 for such distances. And how can Infinet assist in opening an authorized reseller vendor outlet? Maybe you should contact our sales team, because I am not aware about this kind of procedures. Okay, you can find on our website the contact of our sales team and of our support team, and you can ask them what is the procedure, because I'm not familiar with this process. And the last questions that I see here is if we ever tested the 30 and 34 dBi external antennas on any wireless devices. Yes, we tested. We tested the 34 dBi external antenna and it works fine because this is the only antenna that we have as external, 34 dBi external antenna. And for the 200 kilometers link, how many dBis do we need to reach the remote point? Please use InfiPlanar, because if I tell you a value, it might not work in your actual conditions. You must make a plan of the link, and you will get an estimation in InfiPlanar. It is available on our website. It is very easy to use. You just open the application from our website. You enter the coordinates of the two endpoints. You select the equipment, and then a report with the maximum distance with the link parameters and the signal levels and the power levels will be generated for you. What is the best Infinet model to establish a link using reflection when there is reflection? All our equipment is working fine in conditions of reflections because we have features like instant DFS that will automatically scan the spectrum and will switch to the best available channel. And this is available for all our units. So it is not that there is an equipment that is favorized in over the other. All the devices work in conditions of reflections. Okay, in the chat section, if external antennas are used with SMA connectors, how many percent losses should you consider? Generally, it's not related. The packet loss is not related to this type of connection. Just bear in mind that if you use attenuators, for example, you should consider 1-2 dB losses on the attenuators. Okay, so 1-2 dB losses if you are using additional attenuators, but just using simple SMA connectors will not bring you packet losses just because you do this. Is there a difference in the use of the mitigation techniques in TDMA and MINT technologies? The only difference is that polling, which is used with MINT, is better for multipath. Okay, so if you have multipath fading in the area, multiple reflections, it is better to use polling. It will be more efficient. Regarding the other aspects, the other mitigation techniques, they all apply. So there is no specific difference between TDMA and MINT besides the multipath fading. Then we are asked if InfiPlanar is effective on non-line of sight links. If you have a complete non-line of sight link, it will not predict anything. It will just say 0. If you have near line of sight, it will tell you how much of the Fresnel zone is obstructed and what you can obtain, but only for near line of sight. If it is completely obstructed, it will return 0. It will not plan the link. If we have a test report for NLOS reflection or diffraction, our support team should have this kind of information because they performed a lot of tests in all type of conditions with all the equipments in clear line of sight, in non-line of sight, in good weather, in bad weather. So I suggest you contact the support team because they have a lot of reports and tables that show you the results of the tests. I personally do not have this type of results. If all the models from the R5000 family can pair with the Evolution family, yes, they can pair. For scattering, do we need to use maximum power if you have the link across a pine wood? You should use maximum power only if you have problems currently on the link, not by default. So it's not a default recommendation because the link can work fine with the less power, and less power means less interference, and you extend the lifetime of the device. Okay, so use maximum power only if you have problems on the link using a lower power, not by default. If you install a link over a pine wood, you should set maximum power. This is not a statement. As I mentioned, we have compatibility between Evolution and R5000, and you can use them in both situations. You can have an Evolution base station with R5000 subscribers, or the other way around, an R5000 base station with Evolution subscribers. Okay, they are fully compatible. Okay, I think these are all the questions for today. For any further clarifications, you can write to us on email, to me or Bogdan here in Romania, or to the support team. If you have questions related to sales, pre-sales, you should contact directly the sales team, because here we cannot guide you. But for other clarifications, you can write to the support team or to us. Okay. Thank you once again for your time, and I hope to see you again during our next webinar. Have a nice day, everyone.